Good afternoon, and welcome to this opening keynote session of the ESIG 2020 Meteorology and Market Design for Grid Services workshop, being held online on Tuesdays and Thursdays during the month of June. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As most of you know, we were planning to do our annual Forecasting and Markets workshop in Denver this year, but due to the coronavirus situation, we found it necessary to move the workshop online. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make what it is, and we encourage you to become involved. We'll kick off the workshop with a very exciting lineup of 3 outstanding individuals from the US and Europe, speaking in a thoughtful session on market optimization. Regarding logistics, we will have several individual presentations, and we'll hold the questions for a 15-minute Q&A session at the end. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar, with typically a few hundred people on the lines will be muted, so we ask you to use the question box in the lower right-hand corner of your screen. Today, we're hosting the opening keynote session, Thoughts on Market Optimization, chaired by Mark Ahlstrom, President of the ESIG Board of Directors. Mark's day job is VP of Renewable Energy Policy at NextEra Energy Resources, and his night job is ESIG. Mark is a very thoughtful guy, and we're very fortunate to have him leading the organization during this time of great change. He's very passionate about ESIG and spends a lot of time thinking about the incredibly important issues surrounding the energy transition, including market design and optimization. I've known Mark since the early 2000s, initially through our collaboration on wind integration studies, and subsequently through participation in a broad range of UVIG and ESIG activities. Mark is a good friend and a good friend of ESIG. Mark, we appreciate having you here, and I'll now turn it over to you.
Thank you very much, Charlie, and welcome everybody. I hope everybody is safe and well. Thank you for joining us on this keynote session to kick off our workshop for the spring. This topic is an interesting one because we're seeing a lot of interest, a lot of very rapid development on the industry with a wide variety of new resources as we have this transformation of the power grid toward not just more variable generation, but also toward more storage, more hybrid resources, more demand side participation, potentially aggregations of DERs and other ways. And what we will keep bringing up is, well, how many resources should the system operators directly be worrying about optimizing, or should some of these resources like hybrids that we've had a lot of discussion on recently, should those become more intelligent resources and move that level up where, the resources to participate have increasing responsibility to be somewhat smarter or more optimized within their borders. So this is a topic that really was motivated by discussions around this with Professor Mark O'Malley that many of you know. Mark is a professor at University College Dublin and was recently chief scientist at NREL. And he's going to help us today in just a moment by kicking this off with some opening context and then participate in the Q&A. We're going to have 2 speakers. Ed Rothberg is CEO and co-founder of Gurobi Optimization. He's a PhD in computer science from Stanford, and has served in leadership positions in the optimization software industry for more than 20 years. And then next, we'll have Mike Hogan, who's a senior advisor to the Regulatory Assistance Project, advising policymakers on market design and integration of variable resources. He's worked in the industry and for energy policy organizations for 40 years, including development of over 13 gigawatts of independent power projects on 4 continents. He has an MBA from Harvard, a master's in MIT from energy policy, BA in philosophy, and a BS in aero and mechanical engineering from University of Notre Dame. So with that though, Mark, why don't you set some context for us, and we'll get into the presentations and have what I think is a very lively discussion on this topic.
Okay, so welcome everybody. Thank you for those words, Mark. So Mark gave a very good introduction as to where this came from, but I'll tell you where it really came from. On a conference call organizing this ESIG workshop about 6 weeks ago in a forest in the mountains south of Dublin, where I was walking, taking a conference call where we were looking for ideas, of what to have. And, obviously optimization is a very important part of market design. It's also an important part of forecasting as well. And I personally have academically, I've always been frustrated by optimization. Many reasons in expertise, but many ways, sometimes I see optimization and I see incremental little changes on small toy problems, but I just wonder if a lot of this stuff is just purely academic and is not bringing us anywhere. So I'm very frustrated by it. But then I had the privilege of meeting Ed Rothberg in February, and he gave what I consider to be the simplest, plainest sort of talk on optimization I've ever heard. So I thought it'd be worth sharing his views with the rest of you if you're equally frustrated as I am. Another frustration that I have with this whole area is that, we do all this optimization, yet we have, in many ways, a very inefficient system, very inefficient, clearly very inefficient. The main example I'll give is that in a lot of capacity markets, there seems to be far too much capacity in certain places, and capacity costs a lot of money. So there seems to be lots of examples of blatant sort of unoptimization or inefficiencies. And the person who came to mind for me when I thought of that was Mike Hogan. Mike is not a man I'd always agree with, but he's definitely got some really good insights into some of the inefficiencies that the markets have. So I've the privilege of sort of introducing this. I've got no slides at all. So I would like to rename this as Marco O'Malley's frustration session. So from there, over to Ed.
All right. Thank you, Mark. And thanks for the invitation to speak. So as Mark mentioned, I'm the CEO at Gurobi Optimization, and optimization is a pretty broad term. So just to give some context, so what we do is we build optimization solvers. So we do the math. So you build the optimization model, we solve the optimization model. That's kind of where we fit. And what I want to talk about is basically, are you solving the right model? And just to skip ahead a bit, the answer is almost certainly no, you're probably not solving the right model. So, I mean, the models that people solve are, it's a collection of compromises. So there are limits to what you can do, limits to the technology, and as a result, it's always necessary to make some simplifications. And so, the answer is you're probably not solving the right model, but you're solving the right model for right now, most likely. And in that context, it's important to periodically take a step back, look at what's changed. Optimization is a fairly fast-moving industry, and so a lot of times some of the simplifications that were made 10 years ago. So totally different context, totally different trade-offs, and so it's useful to take a step back and think about whether the model you're solving is truly the model that you should be solving given the current capabilities. So actually now, following along those lines, I'm actually going to go way back in time. I'm going to look at a quote from the inventor of the simplex method, George Danzig. And so this question of basically choosing the right model to solve goes back to the very, very beginning. So this is actually a quote from Danzig. At a little bull session at the Pentagon with the Bureau of Labor's Input-Output team, Marvin Hoffenberg suggested that we test the newly proposed simplex method on Jerry Kornfeld's diet problem. Jerry said that he worked on the problem several years earlier for the Army, who wanted a low-cost diet that would meet the nutritional needs of a GI soldier. And so George Danzig was actually hired by the U.S. Army to work on logistics, to come up with better ways to essentially to ship materials, to Europe and Japan, really. This was just after the war. And for pragmatic reasons, basically said, well, yeah, that would be a great problem to solve. But the problem I can actually solve is the diet problem, which is basically a handful of linear constraints, a linear objective. So if you look at the history of optimization, so George Danzig was, of course, working in the U.S. There was actually quite an active effort to advance optimization in Russia, similar timeline. And notable person in this was Leonid Kantorovich, who was he's generally credited as being the inventor of linear programming in 1939. And what was he working on? I mean, he published a book, The Mathematical Method of Production Planning and Organization. So, in maybe traditional Russian style, he was basically trying to optimize the entire Russian economy. So take, all operations of the economy, plug them into one optimization model, press go, and you've optimized the production of the country of Russia. And of course, was that the right problem? Was that the right grain at the time? No, not even close. It wasn't anywhere near practical. So just to give a bit of context about this push-pull that's been around forever, this push-pull affects nearly every industry. So let me give you a few examples. So, in the airlines, so you've got optimization opportunities everywhere you look. And, again, it's a situation where in an ideal world, you would build a model for the operation of an airline. You'd press the solve button and the optimization engine would spit out everything. Flight schedules, aircraft assignments, crew assignments, gate assignments, everything. But the reality is that that's not a tractable model. You have to make some compromises. And so they split the various pieces of their operation into manageable chunks. And so they split aircraft scheduling from crew scheduling. They split maintenance scheduling from aircraft scheduling. Schedule creation. There's a long list of things that ideally would be optimized together, but in practice, it's just not tractable. Similarly, for supply chain, you split production planning from logistics. You split production planning from inventory management. Even production planning, you split it into different pieces depending on at what point you are in the supply chain. And there are clearly negative consequences associated with these splits. In supply chain, there's something called the bullwhip effect, where basically if you optimize each piece individually, they're problems at the seams. They're communication problems. And so a small change at one end of the supply chain can result in just a massive overreaction at the other end. So if I try and bring this back to the electrical power industry, so, what are things that ideally would be included in an optimization model, but, maybe aren't so practical? So one axis where it's often useful to add to the model is to capture more detail. In the case of electrical power, things like combined cycle plant. Sorry for the typo. Where there's some complex behavior going on that's just not being captured universally in optimization models. Another thing you might want to capture is more precision in time, so more finer timescales. So traditional dispatch interval is, I guess, 60 minutes at this point. 15 minutes potentially would be interesting, but it grows the size of the problem quite a bit. I'll come back to that. A broader scope, so maybe you want to integrate the electrical power market with the gas market. Or actually, the one that seems to be present in every industry is uncertainty. So the inputs to an optimization model are drawn from essentially a probability distribution, and ultimately we just pick a single sample from that distribution and use that as the representative for the whole distribution. So it's not really captured much in electrical power. Reality is it's not really captured much in any industry. That's a tough problem. Okay, so in that context, as I mentioned, there are simplifications that are made at a certain point in time, but the technology is a moving target. So this is a slide that shows improvements in the technology. I know it looks like a marketing slide. That's not my intent. I just want to make I just want to be able to say concretely that the technology is moving. And so the red line here, this shows the average improvement across a broad set of test problems from our first version to our current version. And the scale is on the right. So we've in the past 10 years about a 60x fold improvement in average performance across a broad set of problems. So I mean, what that means, of course, is that you can afford to go back and rethink some of the choices that were made earlier because the capabilities of the technology keep shifting. And to make this more concrete, we looked at a set of 70 models from MISO. These are SCUC models, and in the last year, the average performance has improved by 39% across this set of 70 models. So the time to find proven optimal solutions to these 70 models on average is 40% faster than it was a year ago. So there's a desire to add more detail. There's some opportunity, but you can't get carried away. So just to give a bit of detail, so let's say you go from a 60-minute dispatch interval to a 15-minute dispatch interval. So we looked at, basically we created some synthetic 15-minute dispatch interval models. We took the 60-minute models and then we interpolated between the intervals to create 15-minute data points. So the size of the problem increases by roughly 4 times, of course. What happens to the runtime for that optimization model? So the first step in solving an optimization problem is solving the root relaxation, basically setting aside the integrality constraints and just solving that as a linear programming problem. And the cost of that LP from increasing the problem size by 4x grew by 26x on average. And then the time to find a proven optimal solution, it wasn't quite 26x, but it was 11x. And so even something like this, it causes the runtime to grow quite a bit. So it increases the complexity of the problem quite a bit. So I wanted to share some results from a project that we've been involved in recently. This is it's called the Hippo project. It's a ARPA-E funded project, a collaboration between Pacific Northwest National Labs, GE Grid, MISO, University of Tennessee, University of Florida, and Gurobi. And the intent of the project was to create a solution framework for day-ahead SCUC based on parallel and concurrent optimization. Basically, figure out how to use large-scale parallelism to speed up the solution of unit commitment models. So parallelism, of course, opens up a lot of new avenues. And so, one sort of obvious thing to try, given lots of processors, is take the existing problem, the problem you're trying to solve now, and decompose it. Use some sort of standard decomposition technique. There's Bender's decomposition. There's ADMM. There's a number of decomposition techniques that are available. And then use the parallelism. Use multiple machines to exploit the decomposition and speed up the solution. And we in the Hippo project, mainly Jesse from PNNL, spent probably a year playing with different decomposition schemes. And what we found is basically you have to be an artist to get decomposition to work well. So that's a portrait of Rembrandt on the right. So then there's really a clear trade-off in decomposition. So basically, if you're going to decompose, typically what you're going to be doing is giving up a lot of accuracy. So our traditional tolerance in optimization is 10 to the minus 6. So if you specify a constraint, we consider it satisfied if it's violated by less than 10 to the minus 6. For decomposition, it's tough to get 10 to the minus 2 accuracy. And is 10 to the minus 2 enough? Depends on the application. In this domain, our impression was it was not enough. And so the decomposition approach just wasn't an effective approach to attacking these problems. And fundamentally, the issue with decomposition is if you're going to decouple the problem, it has to, the decoupling in the solution technique has to match the decoupling in the underlying problem. So you're looking for ways that the problem is loosely coupled. And if you look at sort of some of the obvious axes for decoupling a unit commitment model. So, as you very well know, if you inject power somewhere in the network, it may show up, in a totally different part. It may affect a totally different part of your network. And, in fact, it could actually affect a part of someone else's network as well. So, there's pretty tight coupling when it comes to injecting power into a network. And then, time is the other natural axis for decomposition. But, as you know, if you turn on a power plant in the morning, the effects of that can ripple throughout the day and potentially to the next day. And so, decomposition just didn't turn out to be all that effective. So the next thing we did was we actually looked at some of the simplifications that have been made over time. And one of the main ones relates to SFT, simultaneous feasibility testing. So basically, the decomposition that was done long ago was to basically avoid integrating the SFT inside the solution of the optimization problem, and instead do it as a sort of an outer loop. So you choose a subset of your transmission constraints that you think are likely to be binding. You solve a MIP with that subset. That gives you a solution. You check that solution to see if it violates any of the transmission constraints. And if it does, you add those constraints in the MIP, you solve again, and you repeat this process 3, 4, 5 times until you wind up with a solution that satisfies your transmission constraints. And so what we did was we looked at how this process could change given the fact that we had lots of processors available. So testing violation of these transmission constraints is expensive, but it turns out that it can actually parallelize quite well. And so, what we did was we took another look at the simplification that was made, the decoupling that was done way back when. And what we found is if we integrated the SFT into the optimization process, so more tightly, so basically we made it essentially something that is a subroutine of the MIP, that actually resulted in, more than a 10x improvement in overall solution time. So what this chart here shows is on the x-axis we have the solution time for a variety of models. Each dot is a model, is a particular SCUC problem from a particular time. And on the y-axis we have the speed up from exploiting this integration, removing this decoupling. And you see 10x plus improvements from rethinking this choice that was made way back when. And then the last point I want to make was when it comes to thinking about the right problem, it's actually fairly common for people to assume that if you're using optimization, it's a black box for finding proven optimal solutions to the problem. And it's a different perspective to view it as basically a toolbox for building heuristics, a toolbox for building domain-specific heuristics. And so one of the other things we worked on was just doing exactly that, building specialized domain-specific heuristics for solving difficult unit commitment models, not worrying so much about the lower bound, about the proof of optimality, just how long does it take us to get a good solution? And so what this graph shows is a set of, again, 70 models, and the time required to find a solution that is 0.1% above optimal. And note that we're not proving that the solution is optimal, or is 0.1% from optimal. We're just finding the solution. And what you can see is a pretty significant improvement in the time to find such solutions. So this is sorting each model by runtime. And the blue line is just the default approach, and the red line is the custom domain-specific heuristic. So actually that concludes my remarks. So I will now hand it back to Mark. Thank you.
Thank you, Ed. We're going to transition over to Mike and then go into the Q&A. If you do have questions that you'd like us to try to cover during the Q&A session, please use the Q&A box, not the chat box, but the Q&A box on your screen. You can enter them there, and we will cover what we can. So, Mike, please go ahead.
Thanks, Mark, and good afternoon or good morning or wherever people are. I've drawn the, I guess, for an engineer's perspective, the somewhat unenviable job of addressing the question of how much optimization is too much. For any of us who've been trained as engineers, who doesn't love optimization? But I guess I'm going to sort of climb up more to the 10,000-foot level and address what, in my experience, is kind of the iron rule of optimization, which is that the benefits that are available are limited by the context in which it's undertaken and the quality of the information that's available. So, sort of asking the question of, what are the benefits you're looking for from optimization? I would posit that there are, broadly speaking, three of them. First being operational cost efficiency. The second being getting the call it the optimum level of flexibility in the system that is appropriate for the mix of resources. And the third would be the longer term investment cost efficiency. But again, what is it that you're optimizing and based on what information? And I'm going to speak to those two issues in the context of the wholesale power system. So a traditional sort of a vertically integrated regulated monopoly environment presents you with what I would call the optimization field, which is basically generation and grids, with, in some cases, some pump storage hydro thrown in, especially where there's nuclear on the system. As we moved towards independent system operators, deregulated or organized wholesale with the field that was available or that needed to be optimized expanded with generation becoming a little less emphasized, and some of that optimization migrating to the expansion of market geography, optimization of market operations, the establishment and development of energy and services markets, especially ancillary services markets, in some cases forward capacity markets, and off down to the lower left, a little bit of limited seasonal peak shaving, usually from a few large industrials. So this is still an environment where the optimization is largely top down and is to a great extent still reflecting operational cost optimization as opposed to optimization on the basis of another class of information. And what I'm going to suggest is that as we move, especially as we move more towards a system that has growing shares of intermittent resources relative to the share of resources that are fully dispatchable, that there's a large potential, a critical potential for a much more active role for demand in the market, not just as a dispatched resource by the system operator, but in fact as an elastic response to market conditions. And so this is what that really looks like. And when I talk about demand response in this environment, I'm not talking about a few large industrials willingly reducing load on a few peak days in the summer. I'm talking about a daily, almost possibly a daily response, and one that is very dynamic, and one that is massively complex from an optimization perspective. This is a typical summer week in a system that was modeled as part of the Roadmap 2050 project, where 60% of annual energy comes from zero cost resources. About 35% of that is from variable resources. The dotted line is the historical inelastic demand curve through the course of the week. And as you can see, it presents some serious issues for optimizing the use of available resources. The solid line is shifted demand to reflect the real-time availability of low-cost energy. Getting to the question of context, this is derived from work that was done for the Power of Transformation project at the IEA a number of years ago. At the top, you see, in both cases, you're looking at a system with the same amount of renewable energy on the system, same amount of variable resources, and the same reliability standard. In the top, you've got a legacy mix of resources with a fair amount of base load, some mid-merit, quite a bit of renewables, and a very small slice of peaking. And what you see is a plant utilization by category that is effectively financially unsustainable, with base load operating at a 62% capacity factor, mid-merit operating at 11% capacity factor, and peaking at a peaking capacity factor. The lower case is where you shifted the resource mix from a much smaller share of base load, a much larger share of mid-merit, And again, these are very traditional categories for generation. We're not talking about a dramatically new category of kinds of generation resource. We're just talking about shifting the mix. And you see a much more financially sustainable utilization rate of resources on the system. So if you find yourself trying to optimize the legacy mix of resources against the historical inelastic demand curve, you're basically setting yourself up for trying to optimize the ability of an Abrams tank to run the Ferrari obstacle course on their test track. And I would suggest that this is a comparison of average annual wholesale prices from 2015 in 5 US ISO RTO markets. And you're looking at differences of more than 2 times between the highest and the lowest, with the 2 highest clearly sharing some obvious characteristics. And you're not going to optimize this problem away. If you look at the resource mixes between, for instance, ISO New England and ERCOT in 2015, they really were not that much different. So there's something else going on here. So I'm going to move ahead quickly and then come back to that, because I want to look at comparing, and I'm going to start talking about the information that's available for optimization and specifically pricing information. So if you look at the way ERCOT, that does not have a capacity market, approaches pricing, wholesale energy market pricing, and specifically scarcity pricing, and compare it to the way PJM approaches it, you see a pretty dramatic difference. The current ceiling scarcity price in PJM is $850 a megawatt hour. They've proposed the huge move of increasing that to $2,000. That has not been approved despite being out there for the better part of 2 years. ERCOT's at $9,000, and of course, a typical residential customer vol value of lost load would be more in the range of $17,000, $18,000, $20,000, maybe $25,000 a megawatt hour. If you look at MISO, you see something similar. MISO has a much higher maximum scarcity price of about $3,500. And again, if you look at the actual or economically estimated value of lost load, it's considerably higher. And so what you're left with, MISO's a little unfair to pick MISO here because actually the MISO has very little to do with the longer run decisions about investment efficiency. But if you look at PJM and you ask yourself, what position does that put you into in terms of trying to translate the information available for optimization into those 3 benefits that I mentioned at the outset? So the red dotted line is effectively the price cap in PJM, and the achieving resource adequacy means that you're left with finding some other way. In the case of PJM and ISO New England, New York ISO, and a number of European markets, you're left with a centrally administered forward capacity market as the traditional option that's been pursued. And you see here the 3 different points. This is a Bill Hogan graph that I like to point to. The 3 different possible scenarios that the central system operator might choose to plug that gap between what prices are going to drive and what you actually need for investment efficiency. The optimal is the level that might reflect the actual customer vol value of lost load. The middle line is the mythical 1 day in 10 years or 2.4 hours per year. And the left line is effectively the one that PJM and ISO New England pursue, which is 1 event in 10 years. And that could be almost anywhere, but here it's about, call it a third of an hour a year, with an implied vol of in the range of $250,000 to $400,000 a megawatt hour. And so what do you end up with? You end up with this as an example. This is these are reserve margins in PJM since the inception of the PJM capacity market. The black line is the NERC reference line for what is the target reserve margin to achieve the 1 day in 10 years. And of course, PJM does not pursue 1 day in 10 years, they pursue one event in 10 years. The blue-green line is the margin if you count only the capacity that is cleared in the auctions. And the red line is the margin, reserve margin, if you include all the resources, including those that didn't clear and the ones that chose not to bid. And this is measured against the load forecast at the time of the auctions. If you measured it against the final load forecasts, these lines would actually be even worse by about 4 to 5 percentage points. So, you can optimize to your heart's content in the system, but it's garbage in and a lot of garbage out. So if you look at what the real costs are and real marginal costs are and that should be driving marginal cost pricing in these markets, the top 2 lines are effectively pretty much all that most people look at in terms of essentially fuel costs, let's call it that, or short-term operating costs of the resources in the merit order, when in fact that's a very small subset of all of the marginal costs that can operate in a wholesale market. Especially if we're talking about top-down optimization, using operational cost data, we're really talking about optimizing these systems on a short-term basis around the top 2 lines, and then basically ignoring the rest of it, or not, either ignoring the rest of it from the perspective of flexibility and long-term investment efficiency, or addressing the rest of it strictly from a supply side perspective, because in the end, that's really all that the system operator is organized to look at. And that might include some peak shaving demand response that is dispatchable. It might even include some very fast response balancing energy products, but it is not going to get at the very wide range of potential roles that the demand side and distributed energy resources can play in optimizing wholesale power systems. Peaking demand, seasonal peak shaving really addresses a small share of just one of the 4 categories of demand response or demand involvement that Lawrence Berkeley Lab looked at when they studied demand response for California a couple of years ago. And that's really just looking at shed or managing contingency events and coarse net load following. And even then, you're only getting at a small share of it if you're focused on capacity resources or forward capacity resources. The rest of it is not only not addressed by a focus on capacity attributes, but is actually, in fact, actively disadvantaged by a focus on capacity attributes. And this is a great example that I like to use. This is a small company based in Indiana called Packetized Energy. They've developed a technology to look at things like heat pump water heaters and electric vehicles, and to optimize their operation against, in this case, the availability of renewable supply. And it's a neat little technology. It works a treat as long as it has the information available to it. This is a level of complexity that I would suggest is far beyond anything that we should even aspire for centrally administered system operation staffs to try to optimize. This is a task for accurate wholesale, either price information or supply demand information that's communicated in some other fashion. So I would conclude that while centralized top-down operating cost-based optimization might have worked well in 1980, as we move towards zero carbon electricity, a distributed bottom-up price-based optimization is going to be required, and that in the end, optimization without good energy price formation creates false precision and the illusion of the expected benefits. So I'll turn it back to the organizers.
Thank you very much, Mike. Mark O'Malley, are you on? And maybe a little clearer phone line here.
Yeah, no,
okay.
Is it clear now? Is it?
Yes, it sounds great. Yeah, why don't you go ahead and start off the discussion for us, and then I do have a number of questions that have come in.
Yeah, no, I can see that. Yeah, there seems to be some sound problems in general on this. But anyway, so listen, I'll just keep myself to two questions really, I suppose. First of all, on Ed, I really like his artist. That's the part that I like the best. I mean, it's an art, not a science. I think that's pretty much what Ed said. I'm not saying Ed is not a scientist, but it's a combination of it. But just to some of your details, Ed, you were saying, you've got, you need more detail, precision, temporal resolution, uncertainty, and you sort of pile those all in, and you can't have them all, etc. And we know that. Just in the context of more renewables, though, and you said that, as things change, you need to reflect back. If I was saying, I'm putting you on the spot here, saying with more renewables, which one of those characteristics becomes more important, or is there any, or does anything change? I mean, do more renewables change? You say, as things change, we need to change. So with more renewables, what do we need to change? Is there any one of those that are more important than the others, or is it the artist again?
Yeah, that's a good question. So, I mean, my first reaction is probably not compatible with just market design, but I mean, in general, in other industries, when you have more uncertainty, what you do is you optimize more frequently. So instead of a day ahead, in other industries, the response would be to have, 4 hours ahead, half day ahead, or, 2 hours ahead.
So is that the basic answer, or what about the interaction between these things? I mean, I'm sure they interact. If I put more detail, I mean, you don't actually know which of these is, they do interact with each other, don't they? More detail, more precision.
Oh, absolutely. Yeah. So I guess on the surface, I don't necessarily see that those. I mean, ultimately, you're dealing with renewables. You're dealing with uncertainty. You're dealing with more uncertainty. And so, adding precision on top of uncertainty, I don't know that the precision reduces the impact of the uncertainty. So, okay. I mean, I guess my answer to that would be that I think that, uncertainty just works against some of these axes and makes it harder to benefit from them.
Okay, so there is some logical things that you can use to pick the right model, etc.
Yeah, I would think so.
Yeah. Okay. So that's my question for Ed. But Mike, you'd be glad to know there's a lot of usual suspects online who are going to ask you lots of questions coming up here. So I'll keep mine pretty straightforward. You're advocating for a more distributed model for the optimization, and you've heard what Ed has just said. Can you, do you think? I mean, this is for Ed to answer as well. Do you think Ed would align with what you're proposing? So you've heard Ed's view. I'm asking you, you're saying more distributed. I'm asking you, do you think, without asking Ed yet, do you think that Ed would agree with you, or do you think Ed will counter you? Ed, you're to say nothing yet.
I think Ed would agree with me. I think I would agree with Ed. I mean, I'm not. My purpose is not to argue against optimization. I mean, we're, PG, and in some ways, my purpose is not to be critical of PJM. I mean, PJM has moved to 5-minute dispatch, and has made it work with nodal pricing on both the demand side and the supply side. And I think PJM has tried to do in some ways a lot of the right things on improving energy market pricing. So there's a lot of benefits to be had from improving the speed of the problem solving. But I would assume that Ed would agree with me that if the pricing information or the operating cost information that he's trying to optimize around fundamentally doesn't reflect the true marginal costs of energy on the system, and is not done fast enough, and is not done in the context of an adequate portfolio of ancillary services that give market participants the ability to manage the risks that they face in that market, then the scope of benefits that can be obtained from optimization gets pretty limited, and in fact, you may even be doing more harm than good.
And therefore, you want to distribute the problem. That's your solution?
Well, I certainly want to distribute the information that's needed to solve the problem to all of those who might be in a position to help solve it.
Okay. Ed, do you agree?
Yes.
Or?
Yeah. Our experience with SFT sort of speaks to this a bit. So optimization is expensive, and so optimizing the wrong problem is basically devoting scarce resources to solving a problem that isn't necessarily going to help you. So when it comes to SFT, basically there was a set of constraints left out of the problem that was had some pretty profound impacts on the solution. And so reintegrating them into the problem led to a pretty significant improvement in the results. And so there are certain things that have to be left out, and this goes back to the art versus science discussion. So for pragmatic reasons, there's certain things that have to be left out. And so is this the right thing to leave out? Maybe yes, maybe no. Ultimately, you have to question that, and you have to experiment. But if you're saying that the pricing information doesn't reflect the reality, then absolutely, doing detailed optimization on inputs that don't reflect the reality probably is not going to lead to a fantastic result.
Okay, Mark Ahlstrom, over to you to manage more questions, of which you've got plenty.
Sure. Well, it's an interesting topic, and certainly something that a lot of us have been thinking about. Some of these, Mike, you might not be surprised to see a few questions came in from Dick O'Neill here in terms of, first on your base load mid-merit peaker type charts. He said, well, that's kind of a first century generation following load. And a number of other commenters also said about this, are we getting into a future, though, where, load will follow generation? And how does that change this whole concept of, the generation stack and how you look at the problem? Particularly a related issue is what is the value of lost load, really under those circumstances?
Well, I mean, that was kind of my point, right? Is that we, whether we are or not, we certainly need to be moving from a world where we forecasted load and scheduled generation to a world where we're scheduling load, or where we're forecasting generation and scheduling load, or some midpoint in between. Another way that I've characterized it in the past is that we need to move from a master-slave relationship between load and supply and more of a partnership between load and supply. And I guess what an economist would simply say is that we need demand to become more elastic. And what is the true vol? Well, I mean, there's a stack of studies as tall as this hotel that I'm in that have looked at that question. But I mean, I think broadly speaking, if people have looked at, just take residential consumer value of lost load, and I would argue that that's the most relevant because residential consumers are likely to be the ones, residential and small commercial consumers are likely to be the ones that are nearly entirely or entirely reliant on the grid for their reliability. And that comes in from zero to which is the value of running your water heater at 3 o'clock in the morning. You could care less whether it runs at 3 o'clock or 4 o'clock or 2 o'clock. To the maximum you tend to see is around $25,000 a megawatt hour. So what you're trying to get at, obviously, is if the real marginal cost of energy at some given moment is, and remember that the table I put up there, which is quite representative, that looked at true marginal costs running from zero right up until $9,000 or $12,000 a megawatt hour. What you're looking for is obviously the loads that have the ability to and the willingness to decide that if prices, whether it's critical peak pricing or real-time pricing, gets to $3,000 a megawatt hour, that they'll just turn their electric vehicle charger off and wait for a couple hours, or the municipal water pumping station is going to just put off pumping, from one reservoir to the next for an hour. the benefits of doing that 20 years ago were pretty darn limited. The benefits of doing it 5 or 10 years from now are going to be pretty significant. But if the information and the attendant financial compensation that comes with that information isn't available or isn't accurate, the services and products that are necessary to make that happen are just not going to be, they're not going to come forward.
Yeah, agreed. And related to that, we had some questions too. I mean, obviously, you showed that there's more than just the marginal fuel cost, going into the value of these services, a richer mix. I mean, we expect to get some of that, I think, from certainly from newer resources as well, including distributed resources, demand side, and so forth. So that's a question for me. Go ahead.
Well, a lot. I mean, we're not talking about it today, but you sort of have to. Is a lot of this then starts to take you down into the world of retail tariff design, which we have not talked about.
Right.
And not just retail energy tariff design, but retail network tariff design as well.
But the other thing that we're seeing that shows up with a lot of the inverter-based resources, and now with storage and hybrids and the possibility of aggregated DRs and so forth, is a lot of very, very fast and flexible, but sometimes energy-limited resources. So, yeah, when you were talking about, bringing at least the unit commitment problem down, closer to real time, maybe a few hours anyway, or several times a day, I kind of question, is that even enough? Because seems to me like this concept of what we could originally call resource adequacy or capacity value, from planning, is increasingly becoming a real-time problem. And you have these flexible resources that can balance in real time, but we may have longer-term energy needs to recharge those. So is that kind of changing this? I know with the, we talk about both the ORDC, Mike, and about real-time co-optimization. With that whole range of different products that you showed at different costs, different values or different opportunity costs, is an ORDC even sufficient, or does it have to be full real-time co-optimization for a lot of those? And how does that mesh with the sort of capacity, more the commitment issue that Ed is talking about?
Well, I would certainly say that and I think we're seeing this, if you move from, say, PAM to ERCOT to the NEM in Australia or to the UK market, I think what we're seeing is that co-optimization and administrative scarcity pricing go hand in hand. And administrative scarcity, co-optimization is kind of critical just to basically set the baseline for what the marginal, the value of the marginal kilowatt hour actually is. But in the absence of active demand participation in the real-time market, and we're not going to get there for a long time, the administrative scarcity pricing is critical. It's obviously far from perfect. I think somebody asked what the real vol is, and the real vol is way higher than even ERCOT's $9,000 a megawatt hour, but you do have to strike a balance in practical terms between, getting real vol pricing versus the risks and the challenges of implementing a $25,000 a megawatt hour price in the traded energy market. But the administrative scarcity pricing does two things. One is within limits, it allows you to make sure that that when you co-optimize, what's clearing is as close as possible to what should be clearing in terms of the opportunity cost relative to the resource or the reliability standard that the system operator is operating to as a proxy for active demand participation. And the second thing that it does, which again in practical terms is extremely important, is that it provides another lever for mitigating the risk of market power abuse. And that's an issue that the Australians are facing in spades right now. They've got co-optimization. They've got a very high, 14,700 Aussie dollars a megawatt hour maximum scarcity price. And some of us, Paul Simshauser and myself, others, would argue that actually under those circumstances, the market in Australia is operating very well. But there's a lot of concern, and I think some of it is quite well-founded, that there is market power operating in the Australian market. And I think they have co-optimization, but they don't have administrative scarcity pricing. I think implementing administrative scarcity pricing would go a long way towards providing an additional level of comfort for stakeholders in the Australian market, that they're not just getting accurate scarcity pricing, but they're also getting scarcity pricing that is the result of legitimate scarcity and not the result of the exercise of market power.
Okay, clearly, if you're not a market wonk here, what you're seeing is kind of why we started bringing market design into ESIG meetings a few years ago, is that it becomes inevitable that as you talk about how you're going to use all these new resources and integrate forecasting operations, you get into market design pretty deeply, right? And it's an integrated issue.
Actually, one comment I want to make. So going back to the example I gave with the 15-minute dispatch causing the runtime to explode. So there's actually a positive side to that story, believe it or not, which is that as the problem grows, the cost explodes, but as the problem shrinks, the cost collapses. And so it's often possible to remove just a small amount of detail and go from a problem that takes hours to a problem that takes minutes. And so, when it comes to questions of, what's the right time scale and how much optimization can you truly do in smaller time scales, clearly you can't solve the sorts of unit commitment models that are being solved today. But it may be possible just to remove a small amount of detail and get to a model that can be solved in a reasonable amount of time, and maybe in balance you win.
And that really hits right on a final question I wanted to ask you here that came in as well, that I've been thinking about, is that with some of these resources having more intelligence, control, flexibility themselves, or being more distributed, we're looking at this as more of a decentralized fleet of capabilities, right? To what extent should the decision-making become more decentralized as well, even if it's not globally optimal? Is it time to just expect some of these resources to be a subsystem that is optimized more fully there in order to make the problem more computationally tractable? I mean, you mentioned that for sure on some things. That's one of the art forms, I assume, and where you want to go with this.
Yeah, and so, our experience over and over is there's a cost to doing that. And so you will get a lower quality global solution. And so it's really this delicate balance where you basically want to figure out what's the right thing to relax, what's the right detail to ignore. And, it may be the one you mentioned. It may be that you want to capture those details and leave out another, a different set of details. It's hard to give a universal answer. It really depends on the specifics.
Okay. Yeah. We've got a lot more to talk about this, but this has been a great session. I appreciate all the participation. So I want to thank all of our speakers. Thank you so much. It's been a great start. A lot more we can do. This is the first of what's going to be 8 additional technical sessions coming up as part of this major ESIG workshop. You'll find a full schedule for all the upcoming sessions on the ESIG website in the events area. You're all invited to attend, and there is no charge. So please check those out and attend as many as your time and interest allows. The next session, which is jointly sponsored with the World Energy and Meteorology Council, is the opening plenary session on Thursday at 11 a.m. U.S. Eastern Time this week. So thank you again for your participation. Stay safe. We look forward to seeing you on additional ESIG webinars very soon. There will be details coming from ESIG with the presentations and recordings of the events as well. So thank you so much. Be well.
Thanks, Mark.
Thank you.